Hello, my name is Andrew Cole.
Hello, my name's Murray.
Hello, my name is David. This is Lab 7 flexure and strain measurements. In this lab, we'll be using strain gauge and uh, to find the strain and elastic modulus of two different procedures. We'll use tools like strain gauge and power source. These tools will tell us the voltage change of the beam when it's under bending. Our goal is to understand how they work and how engineers use them in the real world. Figure 1 is a strain gauge. Figure 2 is a multimeter, and figure 3 is the force and displacement gauge setup. To perform this lab, first we need to measure the dimension of the beam and the material. Then we need to set up our strain gauge and the beam. And we need to cut up the end of the strain gauge wire to expose the inner wire so we can attach it to our power source and the loading machine. Then we test the strain gauge to make sure uh, it works using the power source. And then it's time for us to perform our two procedures. The first procedure is to measure the radius of the half circle foam. Place the beam on the foam and bend it 3 times. Take note of the voltage change uh, from the power source for the 3 bending. Calculate the strain and compare it to the radical strain. The second test is first we need to measure the gauge length 3 times to get the average value. Place the beam onto the 3-point fixture. Calibrate the loading machine. Start a video recording and load the beam till 8 pounds. Uh, then plot our then we'll be able to plot our force versus displacement, stress versus strain, and the deformed beam curve, and then we will be observing the deformed beam curve and find the elastic modulus.
In procedure 1, we use these equations here and the data from our voltage and force gauges. We got an experimental strain and a theoretical strain, and then we got a percent error from those two. Um, on procedure 2, we used this equation here to equation 3 to find the Young's modulus, and we used the stress and strain using stress over strain to find the two different values of the Young's modulus over here. Here we have our two graphs plotted out from our two equations. We noted that the data points in our equations were in the elastic region because they were all linear.
And also with procedure 2, we were able to use equation 4, shown on the screen, to calculate the deformation at various points along the length of the beam. We were able to use this data and create a plot of our V of X, our deformation, versus the length of the beam, which showcased this curve shown in figure 6. For results and analysis, so for our procedure 1, for our trial 1, we received a 17.9% error, a 16.1% error, and then 19.7% error for trials 2 and 3, respectively. Both of these did not exceed 20%, which shows that we have good data, and that the strain gauge is a reliable way of testing the strain in a specimen. For our procedure 2, we were able to use our strain gauge strain gauge information to calculate the Young's modulus. We were also able to use our force and displacement data to calculate the Young's modulus in another way. We compared this to a known value found from the book of 2.4 gigapascals, which translates to 348,091 psi. and we found a percent error of 15% with the strain gauge data and a 14.3% error with our known data. Since both of those were also under 20%, it shows that it's a reliable tool to find the strain and therefore find the Young's modulus of a material. And also with procedure 2, we were able to calculate our maximum deformation to be 0.207 inches. And using the information from our deformation gauge, we found a 0.224 inch deformation. This yielded a 7.5% error, which is again under that 20% threshold. And also, when V of X was plotted against the length of the beam, a concave up parabola was created, which reflects what we saw within the lab. That's the shape that the beam also took when it was subjected to the 3-point bend test.
Our percent errors in the lab for part 1 were due to the multimeter, which was consistently displaying varying data when no additional force was being applied. And then in part 2, inaccuracies while measuring could have been a factor, and the initial calibration of the force and displacement may have been a factor. This would affect accuracy.
Overall, we learned how to find the strain and the elastic modulus of the specimen when it's under bending. Both the procedure works really well on calculating the strain and elastic modulus. The result, both the procedure has the percentage error of less than 20%, which is really good. Method one is good for finding the strain, and method 2 is good for finding the elastic modulus when the material is under bending force.
And for future work recommendations, we said that providing the name or some of the material properties of the tested material would have helped out in our data analyzation, just to get a little bit more accuracy. We also suggest using maybe a 2-camera setup to capture the strain gauge, the displacement gauge, and the multimeter. We found that it was a little bit difficult to read our data because we were trying to capture 3 different sources at once. We also found that allowing the bench multimeter to settle for a longer period of time after we connected the strain gauge was a lot helpful, as when we first set it up, our data or our voltage reading was varying pretty greatly. But after we let it settle for a little bit, it became a little bit more stable. And here are our references, and thank you.